Okay. It's 9:20. I think people are still on the way maybe, and someone came in and went out for a break. But let's start, and then because today we're just going to do some simple vector matrix things. Okay, so to refresh our mathematics, 我们的数学概念这样子。Okay. Now maybe you guys are already very familiar with it, but I think we want to make it so that it is everybody's on the same page. You don't want to assume anything. All right. So you actually have the Blackboard notes from last year. Oh, by the way, yes, of course. Before I start, just to check, I put the video up from last week on the NTU Cool. Okay. And can everyone, if people can access, hey. So I put the video up from last week, and also I've got the videos from 2025, last year. Okay, it should be roughly the same. You can choose to see the videos from last year or this video. Don't waste your life so much to see last year's video and then see the same thing again this video. This year it's like 3 hours each time. Just if you need to revise, then you watch the video. If the video is basically a re-recording of the class, so if you're in the class, then you're fine, and then you can just use it as a kind of a revision. Okay. So this week also it'll be recorded. Over the weekend it will edit, and then I'll put it on the NTU Cool for today's class. But today's class will be about linear arithmetic, linear algebra. We will talk about vectors, matrices, and matrix operations. If all of you are already experts and all that, just bear with the class. What we will do is later we will just go through to use Colab to play around. Okay, it's for a little bit of fun, light fun for those of you who are already very familiar. For those of you who are not, or you were familiar and then you've forgotten, today is more like a refresher course. Okay. And we will go through a little bit basics of vector and matrix manipulation operations, and then we will try it out using Colab. So you are going to need your computers today. Make sure you are plugged in, and we will be using Colab. So Colab is a Google account thing, so you can go to your Google Drive later and then create a new Colab file, and you can follow along with me in class. I've also put my Jupyter Colab in the class notebook. You can open that and follow as well. But I think the best thing is for you to create a new one and then try it out yourself and then play around with it on your own ways. Okay? So today's class will be relatively light again. Okay? We haven't really dived deep yet. Next week, we will then, once we are familiar with all these fundamentals, then next week we will be going deep into the perceptron, which is the very first real neural network that you will be working on. Okay? All right. So before I really start, I just want to check again for last week. Anyone had any questions about the lecture from last week, which was the first lecture, and we talked about the motivation, what we want to model, the biological, motivation there, and then the approach of how we model. Like we do simulations, we have a hypothesized model, which includes the architecture, the activation function, the learning rule, and then the procedures that we go about testing the model. No questions? All good, right? Okay. All right, so let's quickly go through this, and then we'll see how fast we can do this. And then if we are done early, because it's such a simple topic, we can take a break earlier, and then we can ask other questions, or people can feel free to move to other classes. All right, first of all, everyone knows that this is a vector, right? Right? If I write this notation, we know that this is a vector that has 2 units, 2 elements, all right? And in each element, in each position, the value of this vector that we call b, sometimes you might see people write, a vector like this, okay? In our class, because if I keep writing this, it will be very tiring, okay? We'll just assume that whenever I write a variable in small letters, that is a vector, okay? So apart from revising the vector and matrix operations, I'm also trying to get us used to the formal way of writing things, because later on when we talk about the neural network models, I will be, sometimes we'll be using these vector notations and all that. So you will be familiar and you would know exactly the format that I'm referring to. Otherwise, you might get lost. Okay? So if I write a small letter b like this, that means it's a vector. And in this case, this vector has elements 1 and 1. It's size 2 by 1. Okay? Or because it is a unidimensional thing, okay, you can also say it's size 2 or length 2, that it doesn't have the second dimension with size 1. All right? Both are essentially the same. But to note, if you are operating in Python, okay, there is a difference between saying 2 by 1 versus something like that. You might see that in Python, okay? In effect, both refer to the same thing, okay? If you say 2 comma nothing, okay? Okay, size of b or shape of b, right? If you do this and you get 2 by 1, that's just telling you it's a vector. But sometimes you might say it's a 2 something. That just means that Python encoded it as a tuple or as a list or something like that, not as an array, but it is an array or a matrix or a vector. Okay, in the program, it's got a difference, but mathematically, conceptually, it's the same thing. Okay, so let's say I have a vector b, all right, and let's say I have another vector, and let's make this vector slightly different. Okay, 2 by 1, all right. We can represent it this way, but essentially, if you have read the Jordan textbook or the chapter, okay, what this is trying to say is, and we will use a geometric concept. Okay, you can understand vectors like this as a mathematical thing, but it's like there's no meaning, right? Oh, it's just a 1, 1, it's a 2, 1. But actually, you can think of it as that, let me use a, okay, I'm going to draw this. I'm going to shift this down. Give me a second because of the space. Okay, so let's say this is on this axis, this is 1, this is 0, okay? And then this is 1, and this is 2, okay? I can understand vectors actually in the geometric sense, so I'm going to do it such that b okay, b is a vector 1, 1, and that means that b is in geometric projection, b is an arrow pointing this way. Okay, means I move one step in one dimension, and then I move one step in the second dimension. That's what the vector means. Okay, then I can have another vector, and I call this vector c, and c is moving 2 steps in one direction, the first direction, and then 1 step in the second direction. So c is like this. Okay, so this is c, and this is b. So this is the geometric understanding of a vector. Okay, so you might think like, okay, it's just numbers, and then now it's just arrows in space, but you can think of it as a real data point in what we call state space. Okay, and then these are features. You can in state space consists of, that's what this symbol means, are elements of, made up of different features. Okay, I'm introducing to you this way of writing things. We have a thing and a concept that is called state space, okay? And in state space, that it is made up of different features. So in other words, I have a collection of features. These features define the state space, okay? All right, no problem. So let me bring it to even more concrete. So I can have the state of being an animal, okay? For example, I can have a space that I call animal space, okay? What's in animal space? The features that make up animal space? Well, there are mammals, reptiles, insects, etc. And I can also even go even deeper. I can say, well, mammals consist of humans, cats, dogs, all sorts of things, okay? All these things make up the state space of a concept called animal, all right? So if I share this with you like this, if I tell you that actually a vector is a feature or a set of features, and if you project a vector of features into a state space, right, and then it looks geometrically like this, like a 2D plot of arrows, then this, let's say that I have this kind of a square area here defining this state space. Every point on this coordinate, 2D coordinate system is an animal, a different animal, okay? Such that if I am this here, I may be a cat, and I'm here, maybe I'm a dog, okay? But if I have a vector that points here, or if I'm talking about that coordinate, and then later on I have an example of another data that's the same coordinate, right? Then that is exactly the same cat, okay? Or I might be a little bit off, and I'm still around cat kind of coordinate, right? But maybe I'm a different kind of cat, okay? So you can think of vectors and the space geometric representation as a higher level, abstract level, conceptual space, and that is essentially what we call state space, consisting of its features that make it up, its elements that make it up, okay? Any questions about this? Okay. This is important because from the ordinary mathematical representation and in neural networks, we are working with basic mathematical operations, but they represent actually very high-level concepts, or they could be used to represent very high-level concepts, okay? So if I want to say that what makes this location a cat is because this one, for example, maybe this is like has what, 4 legs? The state of having 4 legs and the state of having fur, okay? And then this one, the state of having 6 legs and the state of having fur. So that this is a cat. B is referring to the cat vector or the cat location, the cat coordinate. And maybe C is referring to caterpillar, right? Has 6, caterpillar doesn't have 6 legs. Caterpillar has many legs. And furry, a caterpillar, okay? And so that will be another state. Okay, so you see, it's just numbers to you, it's just vectors to us, but mathematically can be used to represent higher level concepts, okay? And if you see that, then you can see why neural networks and anything that operates like that is actually very powerful because it is about representing information, right, in some geometric way. And then you can use geometric principles, or it operates in geometric principles, and then it leads to certain effects because of the way geometry works. For example, if we understand that B and C are vectors that exist in this space with this relationship like this, right? Then I can suggest to you, then we can derive something called F, okay? Where F is equals to, let's do F is equals to B plus C. In mathematics, can people tell me how to, what do you do here? 1, 1, yeah? Okay. Then, obviously, 2, 1. What's the answer? 3, 2. Okay. This is the mathematical operation. What is the geometric equivalent? What is this doing? Yeah, and then what will be the result? Yeah, exactly. Okay, so actually if you follow this one, right? So do what we did just now, and you will see actually the result also. So if let me expand this a little bit. Go to 1, 2, 3, about here. Okay, and we take that it is 3 steps in the first dimension, and then 2 steps in the second dimension here, right? And it's always relative to 0, the origin. Here we call this the origin, by the way. Okay. You will see that this vector f, which we calculated to be 3 by 2, okay, is actually the, oh, sorry, but my drawing is very distorted. Let me draw, it's not so 夸张, okay, not so high up. Maybe about here. Thereabouts, okay? This is actually B plus C. So this is C prime, okay? And then this is, yes, B prime. Okay, so as you said, right, what is happening is I can take two alternative paths, they're equivalent, okay? I can either take B first, so I can go from 1, 1, okay, plus C, and then so from 1, 1, I move 2 steps, and then, so just to make it more visually proportional, okay? So I can make 2 steps to the right and 1 step up. So effectively, I'm moving C vector size, right? And then I end up at 3, 2. Alternatively, I can also do C. Equivalently, I can also do C plus B, right? Yeah. So it's 2 paths that I can take, but I will always end up at 3, 2. Okay? So summation in vector space and in geometric representation is essentially what we call concatenating or adding 2 vectors together by just following their paths from one vector to the end of that vector, and then from that vector to the end of the next vector, and so on and so forth. And I can keep, I can keep doing, if I have other vectors, I can add, right? And what this will do is, now I have created, I have moved to another location in the state space. And in fact, I have changed my coordinate, right? I'm now talking about if I were somehow to be able to add a cat and a caterpillar together, what do I get? A new concept, or I mean a new location in the state space. Okay, so you think about it. If I'm in a, obviously we're going to use this as a neural networks model, that if I'm somehow able to combine two sets of information, I arrive at a new state, a new concept. Okay, all right. Okay, so this is called vector addition. Very simple, the very first thing to first appreciate. Okay? I'm sure there's no problem here. But I want you to convert from the traditional mathematical understanding to a geometric one. Okay? And because it's a geometric one, you can convert it to a conceptual, more generalized understanding. Okay? All right, next we will have, so if we can do vector addition that way, okay, then we have this concept of average. Hey. Let's see. Can someone tell me? Okay. Let's say this is a scalar. This one. Okay? Or it's a constant. It's just a number. All right? Which is the size of the length of the number of I from 1 to n. Okay? All right. So can you see how that if I write this out, an average, as which we all know, right, from statistics, is the sum of all a set of deviations, a set of values, and then you divide it by that number of the number of elements that you sum, and that is the average. Okay, but let's make this a vector. Okay, so think about it. So if I go back to just now that one, right? So B plus C plus F plus, right? Well, let's just keep it, since we have 3, let's do it this way, right? Okay, so geometrically, can you visualize what's going on here? So if I were to do, so we had B plus C, okay, and F was like this, right? Okay, so this is B, and this is C, and then this was F. Sorry, so F, let me be a little bit more accurate so it's easier to, so F should be, right? Okay, and so I get a new vector, right? Correct? Okay, I will arrive at a new location, okay? And because this is just a scalar, what it means is whatever this size is, the size of the length of the red line, I divide it by 3, okay? And somewhere I will get some new size, okay? Then this will give me some sort of average or a centroid or a kind of a center indication, right? A center scale, a center magnitude of this combination of vectors. Okay? All right? So you can say that this is basically what I'm doing here is a linear combination of these subvector components. Okay? Basically, it's linear combination. So the average is just a linear combination of vectors. Can be construed that way. You can think of it that way. All right? Okay. Next thing. So I just want to also, here, the point here is to show you that if you understand addition just now, vector addition, then then a special case of addition or many different cases of addition, vector additions, right? You might see, right? For example, one example is average. An average is a linear combination, which is a linear addition in this case, and then you scale it, okay? All right, so now I'm going to do another one, okay? So instead of vector addition, we now go to the concept of what we call the inner product. Okay, all right. So let's say we have a vector A, and then let's call this 4, 2, and then we have B, and this is 1, 1 again. Okay. In Python, I believe in Python that's what you do. If you do this function, length of A, the answer will be 2. Okay. All right. So sorry?
Isn't length a root of plugin?
No, no, no. Not the magnitude of the vector, but in Python, the size, the dimensionality. So like A is size 2 by 1 as a vector size. So that's what length here is. It's not about it's not this. This, what you're talking about is the mod of A, which is the actual length of A. You're saying that is 4 squared plus 2 squared, is that right? Yeah, no, not length here is the coding operation, not the scalar magnitude, okay? If I wanted to know the scalar magnitude, I would do mod of A. What he's saying is that, oops. This is 4, this is 2, A is here, okay? Then what is the length? So length, right, in the sense of this is obviously 4 square, 2 square, and then square root. Right? Okay? Right? But that is what we call the mod of A, the scalar magnitude of A, not the coding length of A. That is a kind of to get the size of the dimensionality of the vector. Okay? All right. So do you all know how to get the inner product of A and B? Hang on a minute. Let me check here. Oh, okay. Actually, can you give me a second? And actually, this is a good time to take a break. Yeah, I just realized there's an error in my notes. So I'll come back, I'll look up this one again, and then we'll carry on from here. Okay? I don't want to convey the wrong thing. Yeah. So, so let's take a 10-minute break. Let me sort this out because the notes got jumbled up a little bit here, and then we'll come back and continue with inner product. Okay? All right. Let's come back at 10 a.m. Okay? Yep. Sorry about that. Okay, sorry. Yeah, we're back. Sorry about that. I had to get my notes in order, and I realized why there was a bug is because the way I wrote the notes was more for a coding thing than I mean, I was using a coding thing to illustrate the concept. So I got it now. Yeah. So let's get back to this. The goal here is to so we did addition, vector addition, and we had some implications in the geometric interpretation, what it means, okay? And then therefore now, and the next thing now is, apart from addition, we also have product or multiplication. And in vector or matrix operation, multiplication is a little bit more complicated than standard multiplication, okay? An example here of a multiplication instance is the inner product. What is the inner product? If we do the inner product of A and B, vector A and vector B, the inner product is going to be 6. It's a scalar, okay? Scalar means one number, right? Whereas a vector is like many elements making up one vector, right? So the inner product of A and B is 6. How do we get there? Well, it works like this. So that's why it's important to emphasize not arithmetic, it's algebraic. Okay, so when I say length here, it's not the size, not the modulus, but the coding size, which is about dimensions, dimensionality. Okay, and the length in this case, then, if it is about the dimensionality, then the length of A is 2. Okay, all right, and then from a coding point of view, let's start with. If we want to find an inner product, so I'll show you how to do it from a coding way. I'm going to start with let a quantity called the inner product, okay, let the quantity called the inner product begin with a value of 2. Okay, then let's say when I is equals to 0, all right, the inner product is going to be equals to A position 0, okay? So I'm getting you guys used to the Python way of doing things. A position 0 would be here, okay? And it's a product, same position, okay? B position 0, which is here, okay? Plus inner product, the current inner product. Okay, so this is a kind of a coding loop, okay? Getting you guys used to this way of thinking. So when I is 0, let inner product be equals to 0, and then let I be equals to 0. Then the new inner product is going to be equals to A of I, which is 0, times B of I, which is 0, okay? And if we substitute the numbers in, A of I is 0 is 4 times 1 plus, at this point, the inner product is 0, right? Plus 0. So when I is 0, inner product at the moment is 4. Okay, no problem, right? Then we increment, then let I now be equals to 1 from 0 we move I to the next integer, which is 1. Okay? So then in this case, same thing. Now that I is 1, plus the new inner product, okay, is going to be, what is I1? 2. And B1 is 1, plus the new inner product, which is 4. And the answer is 6. Okay? All right. I'm writing it very, very like tediously. This is a coding way of thinking about it. You will see why in a minute, because we will be implementing this. And this is going to be the same way we're going to approach all the neural network problems. We're going to have a kind of a pseudo-code thing, and then we're going to have to implement it. All right? Because I can, of course, I can say the inner product like this, right? It's so simple. Because we are all used to it. We are all trained in math. So we know right? Because it's, sorry, I skipped a few steps here. Right? In high school math or even lower primary math or whatever, we do it like this, okay? But I'm also trying to illustrate to you how, in one case, we have the mathematical way of, arithmetic way of expressing this problem or this operation. Alternatively, we have the coding way of doing it. So let's just say one day, if you don't have a calculator, because you can do this with a computer program, you can say, hey, Python, give me the inner product function of A and B. And then Python will give you 6. Okay? So we know that this is the mathematical way of doing it, right? And we know that if we ask Python for the inner product function, and we give it that, both of these will get us the answer 6. What I'm trying to get at for you is, imagine today you don't have a fancy toolbox, you don't have Python. All you have is your mathematical understanding of what inner product is and logic, basic logic, that if the inner product is this mathematical operation, how do I instantiate it line by line, loop by loop, element by element? Okay? A lot of the neural network is going to be like that. So you can see how actually, oh, sorry, that therefore this is the key function, right? We just have to loop it for every element in the vector. Okay, so that's the inner product. Okay, the next thing we will talk about is matrix then. Okay, now we come to this notion that, oh, it's getting noisy outside. 下课了, sorry. Okay, so we have now a new vector, let's call it 3, 2, 2, 0. Okay, and this is vector now. If I were to type length, it would report 4. Okay, now try and do this. If we know inner product, okay, oh sorry, and let me give you another element here or another quantity here. And here, just to clarify, this is a vector. This one, I'm going to write it as uppercase. Make it very, very obvious. This is going to be uppercase W. Okay. And I'm going to say this is going to be a 2 by 4. All right. And I'm going to say this is 1, 2, 3, 4. And then this is going to be 2, 2, 2, 2. All right? Can you do this in this dot product or inner product? An inner product is essentially a special case of a dot product, okay? And so because now we are talking about matrices, can you think you can do this one? So this would be a 4 by 1, and this is going to be a 2 by 4, okay? So I'm saying that I want you to do 3, 2, 2, 0, and then multiply it by 1, 2, 3, 4, 2, 2, 2, 2. Can it be done? No. Okay? This does not work. Why? Why? Which number? Okay, the dimensionalities don't match, right? Because this is a 4 by 1 and this is a 2 by 4. The inner, and that's why there's this thing of this inner notion, right? The inner dimensionalities don't match. And therefore, this operation cannot be done. It's not allowed. Some people get hooked up here. It's like, why? I can add any number and I can multiply any number. What's so special about a matrix or a vector just because they have dimensionality? Then I can add those numbers, but then when the matrix is like different shape or different dimension, then I cannot multiply them. Well, think about this. Let's say even if it were a simple vector addition, right? I did say that we can add, just now we had B plus C, right? And that gave us F. Because this was 2 by 1, this is 2 by 1, and gives us 2 by 1, correct? And that is okay. But if I do B plus V, so V is 2 by 1, B is 2 by 1, V is 4 by 1, can I do it? No, right? So this is not allowed also. So actually, dimensionality is also a problem in addition, not just this multiplication thing. And think about it in a geometric sense. Consider the geometry. When I am adding two vectors, we just said it, we are just appending the two vectors together in a same two-dimensional space, right? That's why each vector only has two numbers. But the minute I say I want to add something that is in 2 dimensions, and then I come along and this something is in a 4-dimensional space, or even 3 dimension, right? You find that the addition becomes a bit more complex. It's not just simple linear addition. You have to do some sort of transformation. You have to project the higher dimensional thing into a lower dimension, then you can add that part. But in other words, it's not a simple addition anymore. It's some sort of higher level projection. Okay, so it cannot be done in a simple addition. Vector addition cannot be done when you have disagreeing dimensions as well. Okay, you will have to do some sort of projection at least, right? So similarly, for matrix multiplication or even vector inner product, okay, when we are doing that, we have to, the inner dimensions have to agree, okay? And if they agree, that means that they are on the same basis, dimensionality basis, and their associations, their interactions can be calculated. Otherwise, they exist on different dimensions. You can't talk about how they interact in a fair way. That's why the math breaks down like that. Okay, that's the concept, the rough concept behind it. Right? You get it? Make sense? Okay, so always go back to the geometry. The geometry is really, for us as humans, the geometry holds us, binds us down, And don't just think of all this as just numbers and all that, okay? Think of it geometrically. And that will come in when we talk about the neural networks as well. The geometry of it is important. Okay, so V times W, sorry, V times W cannot be done, but we can do W times V. Right? That was 2 by 4, and then this was 4 by 1, and that was 1, 2, 3, 4. If people know, can you give me the answer? I don't have the answer. 3, 2, 2, 0. How do we do it? Just to refresh. You all have calculator or something, you all can do it. So you do the inner product of the first row and the column, right? So it'll be 1 times 3, what is it? 2 times 2, 3 times 2, and 4 times 0, right? And then you get 2 times 3, 2 times 2, 2 times 2, and 2 times 0. Okay, what do you get? 3, 4, is it? 6, 0, 6, 4. Is that right? Sorry, and then it should be plus, right? Oh, sorry, no, it's the other way around. Yeah, where is it? I should write it the other way around. I'm going to write it the other way around. Otherwise it gets confusing. Yeah. Let's do this again. It should be 1 times 3 plus 2 times 2 plus 3 times 2 plus 4 times 0. Okay, then it'll be 2 times 3 plus 2 times 2 plus 2 times 2 plus 2 times 0. I'm belaboring this. I know this is very, very low level math, but let's go through it for refreshing. 6 plus 4 plus 4 plus 0, and the answer is 10, 13, correct? And then 14. Okay, so what is the size of this? 2 by 1, right? Okay, so just to refresh you, because now the two inner dimensions agree, they are on the same interacting basis, okay, in geometrical terms, and the resulting vector will be the outer dimensionalities, all right? So if anytime you, in your coding, and then you're going to work with a lot of arrays and vectors, if you want to check your code whether it's going to work or not, whether it makes sense or not, this is actually pretty fundamental. You will know that the neural network cannot possibly work if the inner dimensions don't agree. Okay? So that means that you need to do something. You need to do transpose, or you need to do readjustment of the order. Okay? And this is where we come to this principle that we just demonstrated. If I do VW, you can't do this. Okay? Cannot be done. Let me change color. Cannot be done. Okay? But when you do WB, it can be done. This phenomena, okay, is demonstrating that matrix multiplication is not commutative. Okay? Commutative means that you can do it in different order. If it is commutative, then it doesn't matter. VW and WV are the same. Just like addition. Addition is commutative. You can do B plus C or C plus B, both give you F, correct? We demonstrated that just now. All right? Geometrically, it means, so if I go back, when something is commutative, the geometric meaning is that I can take both paths, but I will still end up at the same place. That is the definition of commutativeness in geometry. Okay? In multiplication, that's not how things work. You cannot say that I start here and then I multiply by something, I scale it or rotate it. Really, that's what multiplication is doing, is rotation. If I start here and I rotate there, it's not the same as I start there and I rotate. I'll end up in a different place. Okay? So that is what commutative means. So in other words, for multiplication, order matters. Okay. Why? Again, so again, think geometry. Okay? In addition, we do what we call translation. Okay, we do linear combinations. Linear combination means I have a fixed thing. I just have to move it, in a fixed way. These are all just translations. So it doesn't matter if I go from here to here to here, I still end up here. Or I here, and here, I still end up here. No matter how, I will end up here. Okay? In multiplication or product, what we do is rotation. Okay? And what that means is I'm here and then I'm rotating to a new basis. Okay? That is different from I'm here and then I'm rotating to another basis. Okay? If I'm in another place and then I rotate to another place, right? The rotation is not the same as translation. There's a difference in rotation and translation because of that, if you think about it geometrically. All right? So for that reason, that you cannot jumble up the order. If you want to rotate it to the same place, you have to follow through. There are other rotations that will get you to the same state. Obviously, you can rotate things in many, many different ways, but it is not the exact same rotation order, and then you jumble up the order. That's not the same. So you can't rotate first one way and then move to another place. Okay? So it's the reason why matrix multiplication is not commutative. There's a geometric sense to it. Okay? Got it? Okay. All right, the last thing that I want to convey on the board, and then we'll jump to the more exciting, the collab part, is excuse me, this notation, okay? Okay. When we do the matrix multiplication, right? When we did this one, this is a, if you note, what I ended up doing is equals to the sum of which one was this? This was W and then V, right? So W. So I'm going to call this column I, and then row I and column is J, okay? So that this is I, J, and then V, I, right? Where I is 1. Yes. And then, overall J for I1. So I need to for all columns, for row I is 1. Yes. For all columns, and I is 2. Same thing, right? Okay? Can you understand this, the way I'm writing it? Okay? So what I just did here, right, this long string here, is basically Wij, where I is 1, multiplied by V of J. Okay? Because that's it. And then the next one, V of J, all that. Sorry, V of I, okay? V doesn't matter actually because V is only one dimension. But essentially this is the summation of the products, right? For the first row, so where row is I and I is 1. Then you do the same thing for the second row, okay? Now then when this is expressed this way, this is what we call the arithmetic form. Okay, and in arithmetic form, we can say something like A of I is equals to the sum of, over some k order, let's say, 1, 2, 3, or something like that. Cij. B, K. If I have an arithmetic form of an equation like this, I can say that actually if I construe of A as a vector and B as another vector and C as a matrix, okay, then I can say that A, which is 3 by 1, is equals to, so I have 3 elements here, and then 9 elements in this order, and then, that's it. Okay, and we do what we just did just now, which is that this number, right, is going to be equals to these plus this, right? All this plus together will give you this number, right? Okay, so this operation, and we do it for every row. This operation, when you repeat it across every row, is expressed in this, the arithmetic form. Okay, is written like that. This is the notation style. But when you effectively, what you are doing is what you see on the right. Okay, iteratively. Okay, but this you can see is very unwieldy in the sense that you have to write a lot of indices. You have to say I, J, K, and all that, and then how many times you want to sum over, how many rows to how many columns and all that. So you will find that in a lot of the codes and in a lot of the expressions that we are going to work on later on, we will be using a lot more simplistically vector form, which is simply saying something like this. Sorry. A is equals to C, B, like that. I forgot that we need to do this. Okay? Yeah. All right? So if a question or if a problem comes to you in an arithmetic way, like when you do coding, you have to worry about, hey, how many times am I adding this weight and then multiplying it with another weight somewhere in which array, in which vector. You'll be thinking of it quite arithmetically. You'll be saying like this index, this row, this column, I'll multiply it with this, then I'll add it with that, and all that. It's very hard to keep writing everything in arithmetic notation. We just simply express it as vector form, and it's understood that when you write a vector and this is a matrix, that means iteratively for this quantity, for this variable, okay, for this vector, for this array, okay? Your homework assignment will be asking you to do it this way, and let me show you that, and this is a good time for me to switch over. Okay, so let's see, let me switch over to this one. Yes, okay. So if you go to the NTU Cool for today, linear algebra, vectors, matrix operations, and you take a look at homework 1, okay, here. So this is exactly what I just wrote on the board. This is a arithmetic form, and you have to write a vector equation, okay? Actually, I just gave you the answer. But you can think about it for a different kind of size of matrix and try it out. All right? Okay. So then, if you listen just now, you already know the answer here, but then you have to develop it for the further other questions. Okay? So this is homework 1. Okay? And I've set it, it should be available to you now. Can you all access it on NTU Cool? Okay. And you need to hand it up in 2 weeks' time. I set it the deadline to be, let me see, 27号. Yeah, question. It will be both. You will see the homework. So for example, here you can just write it down, right? The answer is write a vector equation. So you just write it down. What you do is you can type it in a Word document or whatever, and then, to submit your answer. Then, given all of this, what would be the vector form of this scalar equation? So then again, write it down in the Word document, right? Then ask you to compute. Compute, you can do it by hand and in R or any other program you want, okay? And if you do that, please copy your R code or your Python code or whatever, paste it into the Word document, or you can截图, you can take a snapshot and paste it into the Word document. And then, because you also ask you to write by hand, what it means is you type it in like just what I did. You work it out like this times this plus that kind of thing. And then all these questions, and you just say 3A, the answer is yes, no, why, okay? This one asks you to write it out. Okay, so in all of this, I ask you to use R or any programming language you know, it's fine, okay? And then consider 2 matrices, blah, blah, blah. Again, you just answer it in the Word document, and you paste figures in support. Everything, compile it into a PDF and upload to the assignment, okay? All right, now, I'm showing this to you ahead of hand. Again, I'm not assuming people are familiar with coding, so I will be showing you a Jupyter Colab kind of way of doing it, so you can see after, once we are through with this. Okay. All right. Any questions? So this is the first thing to sort of slowly ease you into the what we're going to be doing later on, and it will be much more complicated later on. Okay. So I don't want to jump too fast into it because that will shock you, kind of thing. So we slowly step into it. It will be better. Okay. We get things clearer, because if we jump too fast into it, it ends up like, a lot of people get lost because we didn't put the right pieces in place first, so that you know we are on the same page when we do more complex stuff. Okay, so this may seem very like low level, why am I still doing this in Taita, but it's essential to get everyone on the same page first. Then very soon we will be jumping into higher level stuff. Okay, so based on what I just gone through just now, vector addition, multiplication, the notion of commutative properties, the notion that these are, so this homework will not tap you on that, but we talked about how these are translated to geometric senses. Okay. The geometry thing will come in later in the code, you'll see. Any questions so far? Okay, it occurred to me I haven't mentioned one thing, and it's about the average. Let me cycle back a little bit, and then we'll go to the code. I talked about the average just now as when we linearly sum the vectors. Yeah, sure. When we linearly sum the vectors, and then we have this kind of a average vector, right? We end up with some average vector. And then we kind of like, okay, that's what an average is. It's an average vector. But when we go back to conceptual space, we said that every point in the state space, right? The vectors are different features, right? And express different coordinates in the state space of all these two-dimensional vectors. Okay? So if we linearly sum up all the vectors and then divide them by some scalar, conceptually that's the average. But you note, the average is itself a vector, which means it is a unique position in the state space. So, so what's the average in conceptual sense? It is kind of like a prototype. Okay? So for example, I have a vector of this kind of cat A, and another vector of cat B, and another of cat C. I have many cats, and all of them occupy a particular location in this state space. For example, these are all the cat coordinates and all the vectors I get for cats. And then these are maybe all the vectors for dogs. Okay? All the vectors for dogs. Okay? And I calculate the average, which is I add all these up. All right? And then I scale it or something like that. What the average represents is sort of like a prototype cat. Okay? And a prototype or exemplar, depending on how you want to talk about it. Okay? Right? Because the average itself, the average vector rather, okay, itself, is a kind of is in itself part of within this state space. And what does it mean? Well, its location means if I were to have some sort of consider all the vectors together and then weight them all, then the average vector is essentially another point in the state space, and this point is special because it is kind of balancing all the points that were used to generate it. And so that's the concept of a prototype or an exemplar. Okay? All right? Okay. So enough of let's go to the coding thing. Where was my thing again? Yeah, okay. Okay, so at this point, I will ask you guys to, go to your computers and go to Google Drive if you haven't. Okay, so in Google Drive, let's say I'm just going to have okay. In Google Drive, you want to create a folder or in whatever folder you want. Okay, for me, I have my neural networks folder, and the way to create a Google Colab, which is what we will be using, is if you go to New, create a new file, and then you do here. There should be a Google Colab option or selection. Okay, and if you click that, you will see the like it's a new file, and then it will have the Jupyter Notebook interface. So IPy NB is Jupyter Notebook. Okay, that's the extension. All right, so let me share just a few years ago when Google Colab started, right? There is no Gemini interface, no help. Hey, does yours have it? This Gemini interface? Yes or no? 没有啊。哦，那是因为我的是 special 的吗？ Okay, don't worry. Now I assume 我是没有。Okay, 没关系。Maybe it's because I'm using the school. Are you all using personal account or school account? Personal account, maybe, yeah, for the basic one they may not have. 可能 if you use, I don't know if you all can use 台大 g.ntu Gmail. Can you all use that? 有吗? Maybe if you use 台大的 email, Google email to create, because it will be academic, it might have the AI, that option on the right. But it's not important, because you should at least have this one, right? Do you have 这个 start coding or generate with AI? Huh. This is enough, okay? All right. What I'm trying to say is, previously, there's just no AI here, only start coding, okay? Huh? You don't have this?
No. I don't have the AI German part.
Or even with the 台大 email?
Yeah.
Oh, okay, well, that I don't know. That I can't help you. 那你就要去那个 computer center and complain to them. I don't know. Yeah, but you have this one, right? If you should have this generate with AI thing in the cell. Okay. All right. If you haven't used this before, let me orientate you. Okay. The interface is like this. You have the way this works is basically this is a file, and it exists in, you will see it exists in your Google Drive, right, as a file, all right? And it is essentially a Python, interactive Python user interface, okay? If you have used Python before, you know that Python, you can just run it in your terminal, in your command line, on your computer, and it's just basically some command line text inputs, right? And then you run it, and then it can do calculations and give you outputs, answers or files or even figures if you want, okay? And in the regular Python interface, it's just all command lines, and that's it pretty much, okay? Here though, in Jupyter or Google Colab, okay, which is Google's Jupyter Notebook style, it's very convenient because you use Python commands interactively, you run something, and then when you implement it, you code something, and then when you implement the code, it will immediately give you the output, all right? So there are many features to try it out, but the basic ones that you will need to know is first, that you have a, you see that there is this big frame here at the top. The default state here is that what we call this is a cell, okay? And we can add, you see, you can do an add code cell, okay? And you can keep doing that, okay? And we're not, we're not going to confuse people, but we're going to keep it to the one cell first. So when you see this is what we call a code cell. And then there is a different kind of cell here on the right, and you call add text cell, and you can try it. When you add a text cell, okay, you can see the cell looks different. Okay? And that's because the code cell is for actual code that you will run and actually do computation. The text cell is kind of like markdown, okay, which is that you can add just your own comments or descriptions to help you understand the code better or to work with the code in a descriptive way. Okay, so the text cell doesn't run any code. You can put text in it, or even you can put code in it, but it's not going to be, you can't run it. Okay, only code cells can be run. Okay, and we will be using these interchangeably. So let me give you an example of a very simple code. So before you run any code, you have to connect. Okay, so Google has been very generous. You can just connect to a runtime. What this means is, this is like a document, and you have your code, and you want to run it, right? But in order to run, you need a usable computer with a processor and memory and all that, right? Google right now, in Google Drive, what Google has done is just give you hard disk space, right? So you can upload files and download files. But if you want to use these files, and these files may be codes, if you want to use these code files to do computation, you have to connect to a live processing resource. And that's what this connect does. It is what we call connect to a new runtime. Okay? You can have various settings here. For now, we are not going to worry about it. We just simply click connect by default. And it will say, you see here, it's connecting to a Python 3 instance. What it means right now is Google is using your account and is going to their cloud computer somewhere, physically somewhere else, and it's going to apportion your Colab instance with some computing resource. So when it's connected, you will see that this is how much RAM and how much disk space you have. Google is very generous. It allows you 12 gig of RAM and 107 gigs of hard disk space for you to do your computation instance in this Colab. Okay, does that make sense? Hardware and resource-wise? Okay. This is quite sufficient for most of the things that we will be doing in this class, all right? Both those of you who later on go on to more advanced stuff, you can ask for more. 12 gig is generous, but sometimes you might need things like 100 gig or something, okay? And maybe sometimes 107 hard disk space is not enough. Then you can always pay more money. Google will be happy to give you more stuff if you pay more money, okay? And so this is very handy also. You can see they give you the resource monitor, and you can see like if your RAM, which is basically how many variables information and the size of your variables that are being held in the computer at any instance, if you reach some sort of upper limit, then it will crash, okay? All right, so if you've connected, everyone is connected, then we can try out some very cool stuff. So in Python, basically you need to do, you need to import, we're going to be primarily using what we call the NumPy module, okay? And a lot of people by default, because the way that Python works is that you call these tools and then they will load up the function. You import these tools, these modules, and then you will have the functions, and then you can use the functions. Well, sometimes people don't want to type the full name of the module, so NumPy or NumberPy, okay, Python, then you can just replace it or have it as a shortcut or an alias as NP instead. So this is what we will do. So the first step is to import the library or the module that you need, and let's use NumberPy. And we will this is play button, and if you play and you see this green tick here on the left, means that it was successfully run. At this point, there is nothing. It was just loading up the NumPy library into your session, and you can call it as NP. Okay. So then I can do another code, and I can create a variable. Let's call the variable A is equals to NumPy, NP, and in this function, let's just call it let's put it inside, let's say 1, 2, okay, and if I do A, 1, 2, okay, so what I've done here is I have created a vector called A. You're going to have to open Google Drive and do a Google Colab, okay? Do you know how to do that? Okay. Okay, then NP array 1, 2, now I've created a vector, okay, that is called A, and in A, it is an array which has 2 elements, 1 and 2, so actually it's a vector. Even though it's called an array, it is a vector. Okay, so here is a function to try out. Oops, NP shape of A, and then you play it, it's length 2. Okay? All right. Now, here's the cool thing about Colab versus a Python terminal or a command line. In a command line interface, whenever you run something previously, you cannot change it, right? You just have to keep on running new things or replace the old things by progressing along the command line. In this Colab and Jupyter interface, you can go back wherever you were in the history and change it. I don't want A to be just a length 2 vector 1 and 2. I want it to be 1, size 3, and then I want all the numbers to be 4, 4, 4, something like that. And now I update. Now I try and I play A. A is now a new vector, and then the new shape is 6. Okay? To me, this is the most important feature of Colab or Jupyter Notebook. Okay? Is that you can go back and update it, and then you can change it, like just like that. As opposed to the command line, because the command line is that you usually have to keep going on and on and on. You cannot go backwards and update. It's fine. It's just that after a while, it becomes very cluttered and just repetitive. Here, you can keep things clean, right? I updated the vector A, and I didn't need to have more and more lines. I can keep the lines clean. And it's useful because when I want to convey a notion to someone else, another person, the person doesn't have to deal with all my mess, right? The person can just immediately see things in an organized and cleaned up way, all right? So this is, to me, the most critical feature of Jupyter and Colab, well, one of them, okay? Obviously, the other is that the output is immediately available, you'll see as one of the cell outputs. Okay, so this is just to illustrate to you how to use the cell and a function that is part of the NumPy module. Let's try something else for fun. Let's create another array, and let's call this array B, and let B be 6, 1, 2, 3, 4, 5, 6. Okay. And, oh, sorry, actually, let me say, okay, I have multi-lines. I don't have to do one line at a time. I can do multi-lines. And I'm just going to, after create, report it, okay? And in fact, after create report, tell me shape of B. Okay, it's going to report B, and then it's going to also, it's going to just report the last line, which is the NP shape of B. Okay. Now, then I want to try something fancy. A plus B. What is going to be the answer? Correct. Okay, it just did vector addition there. Okay. Then we're going to do another thing. NP dot product A, B. I believe this should be the way to do it. Okay, which is the inner product, right? Because A and B are vectors. My answer is 90, which is an integer. Okay. Is that correct? 1 times 5 plus 2 times 5 plus 3 times 5 plus 4 times 5 times, and the answer is 90. Okay? All right, so this very, very simple introduction to the critical tool or module you will be using a lot, and that's NumPy. Now, I want to highlight, this is not TensorFlow, it is not PyTorch, it is just basic matrix array operation. So NumPy is like MATLAB. Well, Python in general is like MATLAB, but NumPy or NumPy is the same, is a more specialized tool to deal with arrays like MATLAB. Okay, so it's basic matrix operation. So not any special neural network toolbox that has already been established in Python. And you will find that just with this, we can do already our own neural network. Okay, so this is just a very simple introduction to the Colab interface. Yes, one thing, of course. So these are coding cells. What about text cells? Well, for text cells, you will see that you can insert text cells and coding cells anywhere in between. Okay, so text cells are useful like this. If I add a text cell on top, I can do something like import NumPy module. Oh, why does it do that? Something weird happened to my typing. Oh, I did that. Okay, thank you. Yeah. Huh? Shift 吗？对吗？ Shift, right? Yeah. Very irritated message. Import NumPy module. Okay? And name and use NP as an alias. See, 这个是一个 this becomes a prose, a text, right? And then I just close it. And it's a text. All right? Then let's add another text. And let's say make a variable A, all right, with that is a vector with 6 elements consisting of the numbers 1, 2, 3, 4, 4, 4, and 4. Okay, and I can add, because it's just a basic text, I can add things like italics and bold. Okay, and you can see, oops. So you can make style, font styles, and things like that, all right? Okay, so that's what the text cell does. Okay, here's another tool here to introduce. You can add sections. So if I make this as a header by putting Markdown script, if you guys are familiar with Markdown, hash means it's the highest header, okay? It will appear at the table of contents, right? And here, if I do second order header, hash hash, okay, you will see that it appears indented in the table of contents like that. This will be helpful when you want to organize your code in special ways. So for example, then, here is another thing. You notice if I'm highlighting this second text cell, I can move it down, 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 okay? And I can jump around. If I click on my table of contents, I can jump around anchor points, basically, okay? All right, so just very simple demo of Colab, okay? All right, so that in place, any questions? If that's in place, let's take a look at today's, if you go back to the NTU Cool, I already have the Linear Algebra Colab Jupyter Notebook there. So if you click this link, it will get you to this Colab, which I have shared, which you can view. But I suggest you follow along with your own new Colab, right, to implement these codes below, which will sort of revise what we talked about today, vectors, matrix, and matrix operations, but how to implement them using Colab, using Jupyter Notebook or Python. Because that is what, when we come to making our own neural networks later on in the next few lectures, this will be the main tool, the main interface. So let's get used to this. You can read all this detail on your own time, but essentially what today's lecture is trying to do is revise matrix operations and concepts, the geometric, especially the geometric understanding of it. And you can read that also in detail in Jordan chapter 1986, all linked here, okay? And now to apply all our concepts in a more concrete way, we will use a Colab to test things out, because the best way to understand it really is to implement it and play around with it. Okay, so here, if you follow along, we begin with the notion of what a vector is, okay? And to do that, well, let's create one. And to create one, we use Python's NumPy library or module, as we did just now, NumPy as NP, all right? Okay, then we want to instantiate 5 vectors, each named A to E, each with 2 dimensions, and fill the vectors with integers ranging between 0 and 4. At this point, I already have an example here, but here, let me demo this very cool thing here, okay? I'm going to copy, I'm going to copy this text, copy selection, and I'm going to create a code cell, a new code cell here, and I'm going to use generate with AI here, okay? And it appears here. What can I help you build? Well, I'm going to paste. Okay, I'm going to play. Oops. And it will just do it for you. Okay, so smart. Accept. I'm just going to accept. You can accept and run, but I'm just going to accept first so we can take a look at what it's done, all right? So we gave it the command, instantiate 5 vectors, okay? So, which we did just now, we instantiated 1 vector here, right? Okay, so compare, contrast. 5 vectors, A, B, C, D, E, each named A to E. So pretty smart, it got that, okay? Each with 2 dimensions. So it's got this here, if you understand the function here. It's done some numpy, random thing, whatever it is, okay? Don't worry about it if you don't know. But it's made it such that A has size 2, B has size 2, C has size 2, etc. So yes, it looks like it has 2 dimensions each. And fill these 2-dimensional vectors with integers ranging from 0 to 4. That's what this means. 0 to, first, fill it with integers. We didn't say what kind of integers, what exact integers to fill. We just say, I don't care what integers, right? Integers means whole numbers, right? Can be 1, 2, 3, 4. Cannot be 0.1, 0.2, this kind of thing. So just take whatever integers and put it into each of these size 2 vectors, all right? The only constraint is that these integers must be ranging, the number must be from 0 to 4. So it can be 1, can be 0, 1, 2, 3, or 4. Cannot be any other number. And the way it's implemented in Python is, well, the random randint is to create a set of numbers that start from this start number, and the start number here is 0, and how many numbers from 0, okay, counting 0 in. So if I put 5 there, which is what it did in the next one, it is 0, 1, 2, 3, 4, which is 5 different numbers. So that's what 0, 5 means there, okay? So, and then it very nicely tells us that, well, after it created, that's technically enough, but it will also print it out like this, okay? So if I play it now, okay, I will get an output. Why don't you guys try it yourself? Okay, if you haven't, just copy, tell the AI to do this, paste it, and then like see what's the output you get. You will have different numbers. Every one of you will have different numbers because we just ask it to have different integers. I'm not going to play it because this is exactly what I got here, so I can delete that. Okay, and I'll show you my output is you should get something like that. You should get same number of vectors, each same size, but maybe the numbers are different, but they all should range between 0 and 4. Anyone get anything weird? No, should be very well behaved. This is very simple. Okay, all right. Then next is plot. Use Plotly. You can use any plotting thing you want, but I'm just going to use Plotly, okay? Which is another module, okay, in Python to visualize the vector. So this is kind of what we did. We want to understand these 5 vectors in a geometric sense. All right. So try it. Use the AI, and create your own code. And you paste it. Okay. And this is what it gets, what it gives you. Okay. Now, at this point, you realize I haven't done any coding per se, isn't it? I just use the AI, and then the AI does and then paste it in, right? Okay. Now, I'm doing this because the tools are available now. When we did it long time ago, when we learned it, obviously we didn't have AI to do it. We have to really know the code. My advice to you guys is, depending on how strong you are in coding, don't use the AI, right? Try to come up with the code yourself, okay? But if you find that, yeah, it's so simple, I can use the AI, and you know what you are doing, I am fine with you using the AI, right, like the way I'm doing, and then putting in, using the code and then implementing it. Because at this stage, it's trivial, it's fine, right? So actually, at this simple stage, for at least these first exercise, homework 1, I suggest don't use AI at all. Try whether there's a need for the using coding to do some of the calculation. Try to do it on your own without the AI, okay? The point really is for your own good, not for me, my benefit, I don't care, right? But you need to, if you are not sure, this is a good time to struggle and figure it out, okay? Do it that way. Later on, as things get more and more complicated, yes, the AI becomes more and more helpful because we have limit. At some point, we will be wasting a lot of time for very trivial coding things. Then it doesn't make sense to be worrying about the code. Just use the AI to help you, or use the AI to help solve your coding problems. Perfectly fine in this class, okay? Because in this class, really, even if you use AI to create this code, there will be some problems that the AI cannot help you with. You will find. All right? So I'm just demoing it this way because the point of this class is to get you familiar with the interface, and we don't want to spend too much time on the coding logic and all that. So to let the AI tell us the code, and I know because, and some of you might be having experience in coding, so you will realize that, these are very trivial, and the thing is also when the AI generates something, do you have the experience to judge whether it's correct or not, okay? Right? Because if you don't have experience and then you use the AI and you just take whatever the AI gives you, it might be wrong, and you don't have the experience to判断, to judge whether it's right or wrong. That's dangerous, right? So at this level, and in this case, we are sufficiently experienced. I think it's okay to see because it's easy for us to judge. So that being said, let's see what the AI gave us, okay? We asked it to use Plotly module. And again, you see, if you didn't have experience, you will probably just say, visualize the vectors. You wouldn't know to specify, I want to use the Plotly module. And then usually, in that case, if you don't specify the Plotly module, AI, by experience, I know, AI will use matplotlib, okay? That's another module, all right? But there's a reason why I want to use Plotly module here, and you'll see later, okay? But in any case, and that's because I know of a module called Plotly module, all right? And so this is an example of where if you are a little bit more experienced and you have a clearer idea, then you are using the AI a little bit more correctly and intelligently. So in this case, it has imported Plotly, specifically the function sets, graph objects that is part of the whole Plotly module. So it's not importing the whole thing, it's importing a subset of it. And then it's applying these imported tools with the alias GO because it's a graph object, okay, GO, right? And the way to use this plotting function is to create a figure first and with a handle that is fig, which is itself a variable. So in other words, go.figure creates a figure. Right now, this figure has nothing in it, but then puts this created figure in a variable, okay? The information about this figure in a variable called fig. And then in fig, I continue to add trace, and each trace, which is each object, okay, is the vector A and A1, A0 and A1, B0, B1, C0, C1. And these are all, if you take time to understand this, essentially what this does is to plot 5 lines, okay, which are these five vectors. The rest are about setting the axes and the color and all that, all right? Now, if you're okay with it, I don't know what the AI gave you, but this is what it gave me. And if you play it, you will get this output. Okay, so I'm going to delete this one that we just create. But I'll go back to the one that was created here. You will get this output. Okay, because my vectors are like that, 4, 2, 1, 1, 2, 1, 3, 3, 4, 4, all right? This is what I get, okay? In your case, your A, B, C, D, E are different, okay? And you are going to get different shapes. You guys have it? Can you show me? I'm curious what kind of vectors you all get. Can I see? Yeah, more fun. Wow, that one more fun, more dynamic. Do you have it? Yeah. 对，可以吗？啊。
他每一次关掉重来，他都跟我说我没有在让他，但我每次
Oh,
都
because you didn't do in this one, you got to play it first. 哦，因为你要用 Jupyter 嘛，所以你不是在 Colab， 所以你先。
对，但我每次都有 PIP install， 然后但每一次都打开，他都跟我说没有按到。
哦，你是说你每一次的 instance 的时候，你就还每次要重新灌吗？
对啊。
OK， 通常这个是一个 permissions 或你灌在哪里的一个问题。Right, so the suggestion here is, that's why we use Jupyter. For this class, we use Jupyter Colab, 因为它会解决这一些所有的东西。你要用这个 Jupyter Lab 的话 you feel free to do that, but then that problem is you got to clearly know where you are installing it and what permissions you have. Okay, so I can help you sort that out later, but maybe after class or like offline. But for now, 这样子可以吗？When you 你已经 installed for this session 了嘛 ，right? Then 如果你执行这个，它会 complain 吗？这样可以。好 ，OK. So for now, just try along with the Colab first. I can help you sort out that Jupyter Lab instance maybe later on. Okay. Yeah, if you guys want to use your own platform, feel free to do that. And in fact, it's good. All right. But there might be some other technical issues, and we can sort that out later. All right. But at least for this class, let's use this. Okay, so you'll see, right? Everyone has different vectors, and when you project it, you get different vector visualizations. And that's kind of like what we said, that if it's conceptual space, we might be sampling different data. Let's say this is animal space. Today, you sampled different cats. Another day, somebody else sampled different sets of cats. So, this is like data and statistics, okay? Got it? And this is all represented in vector space, or in state space, okay? All right. Now I want to instantiate 3 other vectors, okay? So you want to try it now? Instantiate 3 vectors named I to j, each with 3 dimensions, and fill the vectors with integers ranging between 0 to 4. So can you do that? So A, B, C, D, E were 2 dimensions. Now IJK has 3 dimensions. So try that out. Okay? So for me, my IJK is 111, 002, 204. 可以吗？ Collab 可以吗？可以哈。Then, similarly, if you have your IJK, which are 3-dimensional, use Plotly to visualize IJK with axes ranging from -1 to 5, blah, 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 0 as the origin. Okay? So in other words, I had a 2D plot here because my vectors were all 2D. Okay? Now try to plot a 3D plot. And this is why I use Plotly, you'll see. Okay? And for me, it generated this. It used go.scatter3d. And then with some of the line settings and all that. And if you want to understand this code a bit better, you have it. You can go back and understand the meaning of the function, what all these terms are. I'm sure you sit down, you can figure it out, okay? If you don't know already. Okay, so if it is okay, I'll show you my answer, and I'll be curious about your answer. But this is the visualization of my IJK. And this is the reason why I want to use Plotly, because it can do this. Okay, Matplotlib will not be able to do this. And I can zoom in, I can zoom out. And you see the significance of this is that, wow, I can see these vectors and how they are distant from each other. It's a very different understanding from the basic arithmetic, isn't it? In arithmetic, we just see them as numbers, vectors, or vectors that have 2 numbers in it, vectors that have 3 numbers in it. Vectors, now think about when a vector has 4 numbers in it. What does that mean? And 5 numbers in it. Okay? All right, so just let me check first. Everyone okay with the 3D visualization? Okay? Anyone got problems? All good? Okay, so let's play around with the idea, okay? When a vector had 2 dimensions, we just said there are it's a feature space consisting of 2 different channels or 2 different elements. So we had in the example on the board that one element location was whether it has fur or not, and then another one was how many legs it has, all right? And that gave us a 2D projection, okay? Now we have a 3D projection. We can still visualize it in this state space because it's a 3D space. And so now we can do something more fancy. We can say, does it have fur? Does it have a few legs or many legs? And maybe a third dimension is, does it have wings? Can it fly or not? Okay? So we are enriching our definition of this animal state space. What kinds of animals now, because now I have more dimensions, I can include more different kinds of animals, or I can understand animals a little better, isn't it? Right? Animals are not just about having fur or how many legs, but some animals might have wings. So I have added another way of discriminating my animal state. Let's think about it even further. Animals clearly do not just have 3 dimensions of features. Animals have so many n-dimensional features. It's finite, right? Animals have a finite number of features, but it's surely a lot of features. So if we project it or translate that back to this notion that you have a 2-dimensional space with 2 features, 3-dimensional space with 3 features. Now we are talking about animals with n-dimensional space. You cannot visualize in our human spatial concept anymore. Okay? You can try to do 4D. What 4D will be is in a 3-dimensional projection of a 4D space, what it is always moving. Okay? The dots are not static. The dots are moving. Okay? To us, they are moving. If you are a 4D creature, it's not. It's static in a 4D space. But because we are 3D, a 4D projection is something that's moving in 3D space. Okay? Practically. Okay? Then imagine 5D, 6D, ND. Okay? So you can't visualize it. But what we can accept is fall back to what I said right at the start. This is a state space. A state space doesn't have to be 2D. It doesn't have to be 3D. It can be many dimensions. The point is that any point, any location in this n-dimensional space is one element, one example, one set of features, okay, that define that coordinate. All right? And why I'm talking about this is because eventually your neural network is going to be an n-dimensional input. Okay? You are going to feed the neural network. You're going to say, I have a n-bit word. If I have a 2-bit word, it'll be 1, 0, or 0, 1, or 1, 1, or 0, 0, what we talked about last week, right? Remember the logic gate, right? Or sorry, the Hebbian rule, 0, 0, 1, 1, 0, 1, 1, 0 last week, right? That was a 2-bit word. You can have an n-bit word, 0, 0, 0, 1, 1, 0, 0, 1, 1, right? A whole string of binary things, okay? We are going to feed this input to the neural network. What the neural network is going to be doing is receiving all these high-dimensional state space feature states, right? And trying to make sense of it. Think about it geometrically. What it is it is figuring out how different dots are located relative to each other, therefore how they are related or not related. And that's essentially what the neural network is trying to do. In a geometric sense, it's receiving all this high-dimensional information, which means that this information is located here, there, or different place, and some of them are related close together, some of them are far apart. And the neural network's job at very simplistic level is to see how to represent this, how to understand it, how to react to it. Okay? All right. So this visualization is important for this reason. It allows us to understand the neural network's functioning at a kind of a more intuitive, visualized level. All right. Next, we will deal, so we've done with visualization of vectors. Now let's try multiplication by scalars. Very easy. So multiply e by 2. Try this. This one you don't need AI, right? Just do e equals to e. Oh, sorry, I did e by 0.5. Let's try e by 2. Oops. Okay. I'm going to play it. Oh, wait, it's going to complain. Yeah. That's because I didn't do it all from the start. I should have. So now I get different vectors. Okay, now play this. And play this. And now I can multiply e by 2. Okay. All right. Okay, so try yours. Multiply your e by 2 and you will see what it does is basically make the vector e twice as long. Okay? All right, no surprises there, very easy. All right, now add two vectors. So add b and d to yield f. Can you try that? So do this. And now you should be smart enough to know that I don't have to have all these fancy things again, right? I can just do fig add trace, whatever, and then fig show. And then it will update. And now I have a new vector f, which is the 3, 4, based on my set of vectors. So you can try it for your case. Okay? So add b and d to yield f. And my b was the red line and d was the purple line. So red line and purple line gives me this new cyan line, right? You can see that's what's happening. Okay? All right, so I hope that you won't just be copying, the code and then just seeing all these fancy figures. I hope you are understanding the. Oh, I see. It's got an error here. I said B and D, and it gives me B and C. That's why it looks a bit weird. Yeah, B and D. Should then give me the red line, yeah, which is way out. Let me see if I can zoom. Yeah, there we go. Okay, yeah. Yeah, so B is this one, D is the purple one, and F is this one, right? Then now it makes better geometric sense. Yeah. So I hope that you can pan it, okay? So I hope that you can appreciate the actual vector values as you are playing around with this. Okay, not just doing the code and then seeing the figure, but you understand and it's making sense to you. The numbers are correct because that's how you check. Okay, now let's try this. Let's try the average. Find the average of the vectors A, B, C, D, E. Can you do that? Because I have a new set, because I just ran it again, so I ran it. Now my new average vector is 2, 4. Okay, so it is itself a location in the new state space. So my average is this place. So find the average. Once you have the average, add the average to the plot with a bigger gray circle and no origin point. So this is what I did here in my next line, line 7 here in this cell. So okay, so A, B, C, D, E, the average is this gray vector here. All good? Make sense? Yes. Mm-hmm. Mm. Oh, because your B and C are, here you are plotting the 3-dimension one, IJKF. So you are, so if you go back up again, because now your trace is fig.show, this one, and this is a 3D one. So if you go back down again, hey, try again, see what happens. Cisco scatter. Hey? Oh, you're in Jupyter, you're not in Colab. Oh, I see. Okay. Let me try run selected cell. S is a weird. Because I think I know what. I think when you pressed, you told it to run everything, not just this cell. Yep. So it ran and it updated. So what this is that figure, this variable, is including all the other figure that maybe is later or earlier. So you didn't like refresh it. So it's adding all this past information. So what you need to do is to create a new figure variable, which is like if you go up all the way to the front, right? Right from the start, we say there, you missed it. Figure dot equal go figure. This makes figure refresh, nothing, right? Then you add the elements you want again, like add trace what again. So you start from scratch for figure.
Like retype this?
Yes, you retype that, and then if you want B, D, and F, then you specifically select, 3 lines, B, D, and F, and then you plot it out again. See, you understand it? You understand the logic? Yeah, give it a shot, figure it out, yeah. But that's the reason why you had that. It's because your figure, the variable is not being refreshed, it's being added. So you got to refresh it. All good? The rest? Okay? The point here is you get the average of the vectors. Excuse me. Okay. So I'll carry on moving first, but the rest of you, if you have an issue, you can troubleshoot continuously. But if the point here just to convey is that, that the average is an example of a linear combination, as we stated just now on the blackboard. So it is a case of a vector that is linearly dependent on the component vectors, right? The average is a linearly dependent vector, right? Okay. And correspondingly, vectors that are independent, okay, are when they cannot be expressed as linear combinations of the other. All right? So in other words, in that case, it's giving us new information because this vector cannot be a linear combination of other existing vectors. Then that's giving us new information. Okay? So, and moreover, an n-dimensional space defined by a set of vectors spanning a set of n linearly independent vectors forms a basis for the space. This is what we're talking about, like the state space of an n-dimensional case. All right? So I'm pushing you guys to think about things this way. It's very important for neural networks. All right, so in that case, to drive home the notion of linear independence, you can tell AI to do this, but you can try it for yourselves to visualize 3 linearly independent vectors, and you plot them. My example here is I have 3 vectors in 3D space. Because I asked you to do 3 linearly independent vectors, you will find you will need 3D space, okay? And the easiest way is to create this. V1 is 1, 0, 0, V2 is 0, 1, 0, and V3 is 0, 0, 1. The rest are the plotting functions, so I won't go through them. But if I play this, you'll see this. And you will see this is the state, the basis state. So in other words, in my concept, if I'm a neural network, and my concept of the world, of the universe, is that all animals either have many or few legs, and either have fur or no fur, okay? My neural network representation is a 2D one. And every animal I see next time will only be I will only understand it as either having fur or no fur, many legs or few legs. This one has fur or no fur, many legs or few legs. And that's all. If I am a neural network and I only appreciate that animals have only fur or legs specification, then that is my state space. That is how I understand animals to be. One day, some God comes or some amazing thing happen. My neural network suddenly gained the ability to see wings or to appreciate another dimension. Then my state space becomes even more complex, a 3D one. Okay? So that my basis space now is a higher order one. And to the extent that I grow and learn, I learned that, hey, animals can be defined this way, that way, and my 3D space become a 4D space, become a 5D space. Okay? However, sometimes I realize that, hey, no, having fur and having skin. For example, I learned that, having skin or no skin, having fur or no fur. Then sometimes I learn, and so that becomes my 2-dimensional or 3-dimensional. I added a skin dimension. Okay. Then one day I learned that, hey, fur and skin seems to be related. You can't have fur without skin. Okay. So that having fur is not independent from having skin necessarily, right? So I might collapse and realize that those two are not separable dimensions, and I collapse my dimension. Don't waste resource to represent higher dimension when only that one is enough. I just have to express the other concept as a function of the other, right? So if I want to say having fur or not, let's just use the skin dimension and then say having, and on the skin dimension, part of it is about having fur, something like that. Because having fur and skin are actually bound together. You don't have to separate them. Okay, so conceptually, that's how you can think about whether a concept and is how it's represented in different dimensions, and mapping it on to a mathematical notion that you have a vector that whether they are orthogonal, independent, or not. Okay? All right. So if you ran that code of 3 independent vectors and you project it, you will get this XYZ in orthogonal space. Okay? All right, so that at the end, and this is to me the funniest line in if you read Jordan chapter. What is a vector? Okay, after you think about all of that, and he states that a vector is an undefined object in linear algebra that has the properties that vectors must have. 有点像废话. Okay, but what he's saying is that a vector is an object. And in this object, it is representing all the properties that define it. Okay? That's really the best way to explain it. Okay? It's important to get this concept right. Okay. All right, so then let's try some other fancy stuff. So let's say we want to do the linear. So we are understanding vectors, definitions, and then linear independence and the geometric sense. So then let's try some operations. So for example, inner product. Okay. To do inner product first, we understand the notion of length. Okay. The inner product of two vectors is the sum of the product of the vector components and is expressed A dot B. So if I have the inner product of A and B, then it's essentially what we did on the board, A dot B, or which is A times B, okay? And it's only defined if they have the same number of components, just like addition, okay? So you try computing the inner product. So here is my coding way of what I did on the board. You all want to try it out on your own. So create a vector you have vector A and B from before. Find the inner product of A and B, but don't use NP dot. Don't use NP, don't use this. See, I did there A and B, right? I did NP dot and I got the answer, right? Okay, don't use this function. Use just basic coding loops. And what I did just now on the board is exactly that, right? I started with letting a variable called inner product start out by being equal to 0. Then for I equals to, this is a function, you can Google it or you can AI it, okay? Gemini it, ask Gemini, range length of A. That is why I said the length in the Python sense, length of A in this case is 2, not the modulus of A, okay? So means for I in range length of A means I do it 2 times, okay? Count I 2 times, starting with I is equals to, because Python default, it starts with 0, okay? So for I in range of length A means when I is 0 at first, do something, then after that is done, then let's move on to I is equals to 1, do that same thing, and then that's it, right? 2 times, because length of A is 2. If A were 3 or 4 or 5, then it would do it 3, 4, or 5 times, okay? So this is what we call for loop. So for I in range, length of A, do this. Make the inner product variable, which remember started off as 0, okay? Whatever inner product variable was, the value was, add to it the outcome or the solution or the answer to A of I times B of I, right? So going back to the blackboard example, if you find it hard to visualize or understand what this line is doing what I did on the blackboard. A whatever times B whatever position, okay, plus whatever inner product was at the time. This new result, do it one more time. Now A1 times B1 plus the new updated inner product. And then inner product will get incrementally added. And the result will be the inner product of A and B. In this case, my answer is 12. And again, don't be satisfied with this output. Go back and check. Go back to your code early on. Look at the vector A that you had, because it's different from mine, and vector B that you have, right? And you know how to compute inner product by hand. The homework will ask you to do something like that. Do it by hand and see if the answer agrees. And if you are curious, here, you can do the same thing like that, right? I don't know why it's taking so long. Maybe Google 当掉. Okay, 12, okay? Oh yeah, I did it. It's right here. Okay. Yep. So I don't need this. It's confusing. Okay. So yeah. So NumPy equivalent here, right? And plus I added something fancy here. So and you will find it useful later on also, because when we run our models, we will be computing something, but we want to take the answer and report it in a table or report it in a particular form. So I have here this thing where you say, instead of just doing the inner product only and then just giving the answer, put the answer in a meaningful way. So you print the text, inner product of A and B, then colon, and then the answer, which is 12, inner product. Okay. All right. I didn't talk about this just now because I feel like this makes better sense when we are able to visualize it like this. Is that note actually that the angle between the two vectors A and B is also has a relationship in terms of the correlation and similarity. All right, this one will come in with this widget demo that I'll show you. All right, have this notion here. We have a dot product A and B, which is the sum of AI times BI for I in range length A. This is actually what I did just now, NP dot. Okay, so you can see there's many ways to do this. This one takes 3 lines to do the inner product. This one does the same thing, but in 1 line. Okay? So if you go to those coding Olympiad, right, this one will win the prize, the other one will lose the prize. Okay? Right? You do it in shorter lines, right? Yeah. So then the challenge is always to like, how can you make your code so efficient that you only need 1 line and you will do a very, very complex thing. Okay? That is fun. Sometimes you get a kick. It's like, it's not just, oh, I can solve this problem. It's, can I solve this problem in the fewest possible lines? All right? And that would be amazing. Okay, so then this is where we come to your notion of, just now you asked, the length, the real modulus length of A or B. Okay? And here, this line does the A square, AI, the square of the 2 components, then sum it and square root it, right? Similarly for B. So here we have the magnitude of A and magnitude of B. So in other words, the vector has a direction, but it can be long and short or short, right? So this magnitude is how long A is and how long B is, okay? I don't need to go through this with you. You guys know trigonometry, right? 就是那个 triangle 三角, right? A square, B square, C square, square root. So this is what this is doing, okay? So now, if you apply this cosine function, which is the cosine of the dot product, okay, which is just now the inner product of A and B, which is, for me, was 12, divide by the magnitude of the length of A and the length of B, the modulus length of A, the modulus length of B, the answer is an angle, right? Because 就是 like 三角啦, right? We can draw it out here. Yeah, do it in red, right? Oh, sorry, I don't need to do that. Okay, so dot product is cosine is adjacent over hypotenuse, so it's B over A, right? Okay, this is capturing that trigonometric relationship. Okay, you can the chapter goes into detail about this, about how this is actually when you do two vectors, you are defining the new basis states spanning these two vectors. Okay, and then when you between the angle between these two vectors, right, is you can compute it using trigonometry, the cosine theta. And in fact, this concept is just like correlation. Okay, correlation, you guys know correlation, the formula is basically between x and y is equals to covariance x, y over variance x, variance y. Okay, and correlation ranges between -1 to +1, right? Okay, the cosine theta, cosine ranges from -1 to 1, right? And the idea is actually the same thing. When two vectors are exactly the same, so if a notion of x and y, they are exactly the same, cosine theta is of the angle between x and y is 1. They are exactly correlated. But x and y can also be anti-correlated, right? So cosine theta of when the two vectors are exactly pointing in opposite direction, 180 degrees, is -1. Okay? When the two are orthogonal, okay, cosine theta of 90 degrees, let's say you have two vectors like that, then it's 0. It's not correlated. Okay? So this is trying to show you that if you have two vectors, A and B, the angle between them, okay, is a relation to the correlation, which is a measure of their similarity as well. In this case, it is measured in radians if you do it this way. All right? You can convert it to degrees or whatever. But then this is a measure of similarity, which is related to the measure of correlation. In fact, it will be correlation, but scaled in some other way. All right? So this is just to highlight this to you. Because, let's go back to the notion in neural network dimension space again. Remember, every vector is a location in the state space, right? So I have a cat, I have different cats, and then I have an average cat versus I have a dog, different dogs, an average dog, okay? If my vectors are all cat vectors, they are all pointing in roughly the same direction. So obviously, these vectors will have a very small theta, small angle between them, right? So they are very similar, okay? And if I have many dogs, then the dog vectors will have very small theta between them, right? But the dog vector and the cat vector will have a bigger theta angle, less correlated, In fact, well, they are more correlated than they are to something else, right? That it's not an animal, let's say. So then that will be not correlated. Okay? So this, again, comes back to this mathematical concept, but you project it to this kind of a conceptual space. They are actually all very much related. Okay, so let's play this. You have my Jupyter, my Google Colab. You can copy this one if you want. If you followed all the way up to here, you will have the same variables. So copying this into yours will work probably. Or you could try, because I can use a prompt here. I gave you the prompt here. And the prompt is to use matplotlib, create a widget with sliders controlling the values in A and B, update the plot for A and B, deleting the previous plot. This is not a good way to be writing the sorry. Very small. 不能 go to the next line. Never mind. Let's do it here like this. Okay, like this. All right. This makes it easier to see. Okay. So the prompt is this: use matplotlib, create a widget with sliders controlling the values in A and B, update the plot for A and B, deleting the previous plot, include a cumulative plot of the iterative change in inner product of A and B. Okay, so this is very complicated already, and I don't expect you guys to, if you're not, if you are not used to working with code, then this becomes a bit higher level. But again, the code is there. You can take time to look at it. I'll just let you know that what this means is I have created a definition, which is a function. And this function is called update plot. So it doesn't do anything immediately, but it will take whatever variable values are A0, A1, B0, B1, whatever you put here like this, these 4 numbers, it will take these 4 numbers, and then it will do this create array, calculate the inner product, and then add the inner product values, and then plot it out. Okay? What this will do is here. Oh, let's see. Here we go. Here we go. Let me make it smaller. Okay, can you see the whole thing? Okay, all right. So if you play this function or this code cell, you get this nice widget. All right. So I have a vector A, and I make A to be 4, 1, and B to be 3, 3. Right? You see that here? Okay. Then and then I calculated the inner product is 15 in this case. Okay. Then the cumulative inner product so far is, at first is it should be 15, but I go down. No, now it's 15. At first it was 16. Now it's 15. Okay. Then let's try it again. Okay, yeah, you need to see the whole thing. Oh, 是这样子的. It doesn't show you the whole thing. Never mind. Okay, so now I'm going to make A1 even more different. And even more different. Okay? And then I make this. okay? And then I make them exactly the same. Okay. So take a look at what it's done. All right? So it's basically the cumulative inner product shows that as I am cycling through my vectors and then they are making them more or less the same or different, right? The inner product is either becoming less different, more similar, or becoming more and more different, or becoming less and less similar. So this is what I mean. It's like a cosine, right? You should, as the angles are rotating relative to each other, either the inner product is going up and down. It's like a cosine wave, depending on their angle. Okay, so this is what I mean by the relationship between the two vectors, the theta, and a measure of their similarity. Okay, this is important because in the neural network, again, we just talked about this. Neural networks are receiving the inputs, which are these vectors. And if the vectors are very different, they are orthogonal, then my state space will have more and more dimensions, right, or orthogonal dimensions. But if the vectors are correlated or similar, then to that extent, I don't need to expand my dimension, right? They are similar information, okay? So that's for inner product. Okay, you have this, you can go back and play with it, and then you can understand it better, okay? All right, the last part is the matrix array part. And here, instead of, so with vectors, we have been using arrows. It's easy because vector is an n-dimensional vector is, if a two-dimensional vector is an arrow in two-dimensional space, right? A three-dimensional vector is a arrow in three-dimensional space, and so on and so forth, okay? So we can draw arrows for vectors. But when it comes to matrices, we have n rows by m columns. It becomes hard to draw this out as arrows, or to at least think of it as arrows. The correct or the more appropriate way to visualize matrices is like that. So to generate a matrix, so I'm going to do this one. Oops. Create a matrix W. So here, create a 2x4 array named W, filled with integers ranging from -5 to 5, and then use plotly to plot heat map of this array, and specify the colors, red to blue color scheme, making heat map 400 by voxel, you know, these are all just settings, all right? So I'm going to implement this, and this is what it's done, okay? So a 2x4, all right, 2 rows, 4 columns, ranging from -5 to 5, right? Yeah, everything is within -5 to 5, right? And they are all integers, okay? So no float, no decimal places. And then having a color scheme of negative is blue, positive is red, like this. And this is what we call a heat map, okay? So in other words, my array is -3, -4, 3, 3, 1, 0, 3, -1. So this is, instead of a vector being one line, now I have a heat map showing me the values of all the elements in the matrix or the array, okay? This is again important because subsequently in neural networks that we will be working with, there will be arrays and you need to visualize them, okay? So this is how to visualize them using heat maps. Now create a vector V of size 4, fill it with integers, blah, blah, blah. We've done this before, okay? So it's a vector. Now we will, so we have an array W and we have a vector V. Now we can do VW. So try np.vw. See what it says. Right? It like crashes, can't do it. Because np.vw, where w is 2, 4, and v is 4, 1, vw, it doesn't work, does not compute. But now try wv. Ah, it gives you a nice answer. -2, -7, -2. Okay? Makes sense, right? We talked about that on the board just now. Just implementing this easily in the Python way. So now I went lazy, I went to use np dot. But if you coded your function just now well, you could use that old function and do the same thing. Okay? All right. So this is matrix multiplication. Now let's visualize the above dot product operation. Okay? And the prompt here is use plotly subplots. What this means is you can have one plot, but in each plot you can have subplots. Okay? And plot V transposed as a heat map. So the vector becomes a heat map. Okay? In the upper left, W as another heat map in the lower left, and U, which is the output of VW or WV, in the lower right, and it will be another heat map, so that you can see how the values of V, the values of W result in the values of U. Okay? And if you play this out, this is what it will look like. Make it smaller here. Okay. V, 4310. W, -3, -4, 3310, 3 minus 1. And if you do V, WV, you get U, which is -2, -7. And the color scheme fitting the scale of the numbers. Okay. Why this is helpful is because when you see it as a heat map, okay, sometimes seeing numbers, the numbers don't make any sense, okay, or very hard to understand the numbers intuitively. But you can, if you see heat maps, you know, for example, when I went to do at the neural network, then you know that, oh, this input or this vector is on these features very important, on these other features not so important. And when I pass it through my neural network weights, in which these weights are these few weights here are very strong, these few weights here are very weak, the result is that my output will be weak here and strong there. Okay? So with the color and heat map, you can get a faster appreciation of the information dynamics that is happening. Okay, so I show this as an example to you this way. We will be using this when we actually do the neural networks later. But you see here, if I were to draw a neural network with 4 input layer unit and 2 output layer unit, which is basically 4 input layer unit, so V is a 4 input layer unit, and a 2 unit output layer, U has a 2 unit output layer, all right? If I implement this here, this is what I will get. Okay? 0, 3, 1, 0, 1, 3, 4, minus 2, minus 7, okay? Which is this one, right? 4, 3, 0, 1, 0, and minus 2, minus 7. Okay? This one is V, this one is U. Can anyone tell me where is W? Huh? What? The edges, the lines, the gray lines, right? You see count how many lines there are? 8, right? 2 by 4. So the number of lines here is equals to the number of cells in W, number of elements in W. So actually, I didn't put it in, but I can tell the program, I should, to say on each line, put the value of W that corresponds to the V unit and the U unit. So if it's like V is 4 and U is minus 2, it should be coming, if U is minus 2 comes from 4310 multiplied by minus 331013, right? So yeah, this one is coming from these 4 multiplied by these 4 W's. And this one is coming from these 4, but multiplied by these 4 W's and summing it. Okay? So here is the very first neural network instantiation. Okay? And you will see this is how I went from vectors two arrays, and then with dot products, okay, and with visualizations, you can get from this basic numbers to this is a legitimate neural network. Okay, we will be dealing with this more later on, but for today, this is the point here, is to get you to familiarize with vectors, matrices, matrix multiplication, to familiarize with the Jupyter or the